In this video, I want to go through question number 4 on page 6 of your practice and notes for potential energy diagrams. This is going to be a two-step reaction mechanism, and it will be a little bit of a different diagram because of that. So this isn't on your note sheet, but I just wanted to talk maybe a little bit about what a two-step reaction mechanism is. Mechanisms are just the steps that make up an overall reaction. So if I looked at the overall reaction of nitrogen dioxide, NO2, combining with carbon monoxide, forming nitrogen monoxide and carbon dioxide, if we broke it down and studied it, we'd actually see it isn't just these two things coming together to form this. It does take place into two steps that are really in sequence or a chain reaction off each other. So the first step involves NO2 combining with another NO2 to form NO3 and NO. And then the NO3 that was formed here combines with carbon monoxide to form NO2 and CO2. So we can look at Hess's law, and we can add up these reactions. We can cross out the NO3 here and the NO3 here, the NO2 here, the NO2 here, and we can actually add those up to equal this overall reaction. Now notice the term slow and fast. It's a chain reaction process, and this is the step that slows things up. This thing proceeds as soon as enough stuff is there. It pretty much reacts very quickly. But this is the bottleneck or the slow step there. With that in mind, let's just look at the potential energy diagram below. It says the reaction mechanism for converting A to C involves how many steps? Well, there's two humps, so it is 2 steps. Each step is represented by a hump or an activation energy. Let's see. Is A to B or B to C the rate determining step? We're going to learn more about rate determining steps, but for now it is the slowest step in the reaction mechanism. So what's going to take longer to climb if you're going from A to B and have to climb hill Y from 0 to 35, or B to C when you have to climb from 15 to 20? Well, the height of the hill A to B going from here to here is going to be bigger, so that will be the rate determining step. Let's see, is the overall reaction in the forward direction endothermic or exothermic? Going from lower to higher, A is at 0, C is at +5, so it's endothermic in the forward direction. Letter D would be exothermic in the reverse direction, going from C to A. What 2 points represent activated complexes? Or is it activated compli, or whatever the plural of that would be? Well, the activated complex is the point of collision when old bonds are breaking, new bonds are forming. So at the top of each hill, you'd have an activated complex. So point Y and point Z would be activated complexes. And then it says, what point represents the intermediate? So point A is the reactants, point C is the products. B is really a step, that in-between step. And notice an intermediate in this reaction would be the NO3, which is formed in one step and then used up in the next step. So that's what an intermediate is, formed in one step, used up in another step, and is kind of a semi-stable resting point in that reaction. So this is just a little bit about a two-step reaction mechanism and some of the adjustments you make from a one-step reaction mechanism in potential energy diagrams. One other thing I thought we should look at is just the terms on page 1 of your homework packet, and just want to make a few comments about those. So in order for a chemical reaction to occur, molecules have to collide. But not only do they have to collide with enough energy for old bonds to break and new bonds to form. And what's that minimum amount of energy they need? That is the activation energy. Now, we talk about effective collisions because not all collisions will exceed the activation energy. Only effective collisions, the ones with enough energy at the right angle where they collide, leads to the formation of products. So you have to have enough energy for the old bonds to break, new bonds to form. and those are the ones that exceed the activation energy. The activated complex is another term, and we talked about that. The point of impact, where old bonds break, new bonds form. It's all the molecules stuck together before they separate after the collision, a very, very unstable spot. The reaction mechanism is the steps or sequence of steps that makes up a chemical reaction, and a lot of them are multi-step processes, and we showed that just in that example with number 4 that we just showed earlier in this video. An intermediate is a substance produced in one step of the reaction mechanism and consumed in the other spot. Consumed in another spot, and the NO3 was an example that we just demonstrated from this diagram right here. Formed in one spot, used up in the next spot, or it's this in-between point right here. Activated complexes up here, very unstable, intermediate, semi-stable spot right there. And finally, the rate determining step is the slowest step in a reaction mechanism. And in this case, it would be this right here. We're going to later find out that these are chain reaction things. So the only way to speed up really a chain reaction process is by speeding up the bottleneck or the slowest step. Kind of like the only way to increase the amount of product is by increasing the limiting reactant when we're working with amounts. So the rate determining step is like the limiting reactant for time.